Okay, so now that you're getting pretty good at the conservation of momentum questions, we're just going to add one tiny little piece, and don't stress, it's really not too complicated. But there are really two types of collision. Type 1 is called elastic collisions. And type 2 are brilliantly named inelastic collisions. And whether or not a collision is elastic or inelastic is all dependent on a quantity called kinetic energy. And now we haven't done energy yet in this course. It's actually coming up. We'll be into it by next week. So you don't know that energy is measured in joules, and you don't know that kinetic energy is energy of motion. Energy of motion. So anything that's moving has kinetic energy. And all energy, just like all forces were a capital F with the subscript denoting where they came from, all energies in our courses will be a capital E with the subscript to tell us which kind. So kinetic energy is capital E with a K. And its formula, because it's energy of motion, is equal to 1/2 the mass of the object that we're talking about times its velocity squared. So this is the equation for the kinetic energy of a particular item. And like I said there a minute ago, and I didn't write it down, energy is measured in joules, and that's a capital J. Okay? And so when we talk about is a collision elastic or not, well, we know that momentum has to be conserved because momentum is conserved in every collision, whether it's elastic or inelastic. But the question is the kinetic energy conserved? If the kinetic energy is conserved along with the momentum, then the collision will be elastic. If it isn't, then the collision is inelastic. So elastic collisions, both momentum and kinetic energy are conserved. Okay? Whereas inelastic, momentum is conserved, but kinetic energy is not. So if kinetic energy isn't conserved, then where does it go? We often say it's lost. It's lost to other forms of energy. Like a car crash is an example of a collision. You often hear a car crash. If you hear the collision, then it's going to be an inelastic collision because some of that kinetic energy is turned into sound energy. Lots of times kinetic energy is used to crumple the car, and therefore it's inelastic. Some of it is lost to the crumpling. In our lives, really, most collisions fall under inelastic because most collisions result in a noise. They often result in crumpling. So most collisions are inelastic. Certainly car crashes, unless you have some kind of a rubber car, two rubber cars, huge rubber bumpers, you might get an elastic collision out of that. But most collisions in cars, etc., would be inelastic. Where do we see elastic? In our lives, the closest might be billiard balls, pool balls. But if you hear them hit each other, then that means they're not quite elastic. They're losing some energy to kinetic, some energy to sound. Where we would most often find them would be on the subatomic level, where we're colliding, like maybe in a Large Hadron Collider in a particle accelerator like we have, where we're studying what atoms look like, and we shoot like a proton at an atom. The collision there would be elastic, both momentum and kinetic energy would be conserved, and mainly because those collisions are done in a vacuum. There's no air molecules there to get in the way. You might also get an elastic collision in outer space. Certainly you wouldn't lose anything to sound, but you could still lose things in outer space to deforming the object. So there's no guarantee that all collisions in outer space would be elastic. Okay, so what does this mean? If kinetic energy is conserved, then it would be the kinetic energy of the first particle, so 1/2 m1v1 initial squared, plus the kinetic energy of the second particle, 1/2 m2v2 initial squared, would have to equal the kinetic energy of the first one finally, 1/2 m1v1f squared, plus the kinetic energy of the second one after the collision. Okay, so how do we do this? Well, we still have to use the momentum equation to find the unknown value that in the question, just like we always have. And then after we know all the m's and the v's, then we plug it into this one to check to see if the two sides are equal. And if they're equal, it's elastic, and if they're not equal, it isn't. So, for example, let's suppose we have a 0.25 kilogram billiard ball, and it's initially moving, so V1 initial, 5 meters per second. It collides with a stationary 0.8 kilogram steel ball, so V2 initial is 0. If the billiard ball bounces directly back, so V1 final is 2.619 meters per second, it wants to know, is the collision elastic? Well, before, we can't just go right to our kinetic energy equation. First, we have to find V2F. And to find V2F, we have to use momentum. We can't use it. We can't find it in the kinetic energy equation, because then we'd be assuming this was an elastic collision. So we have to find it in our momentum equation. M1V1 initial plus M2V2 initial is equal to M1V1 final plus M2V2 final. So you start these questions exactly the way you've started all of them. V2 initial goes to 0. We're looking for V2 final. So bring this term over. M1V1 initial minus M1V1 final, and divide by M2. And now fill your values in. So V2 final will equal 0.25 kilograms times 5 meters per second minus 0.25 kilograms times negative, because it said the opposite direction, 2.61 meters per second. It said it rebounded, divided by 0.8. And when you do this, you get a V2F to equal 2.3809, I can't see, 09375. Works out to be positive, which means original direction. Okay? So now we take this, and when you're finding if it's elastic or not, make sure you don't round too much, because you don't want to get to the end and not know if they're not equal because you rounded too much, or they're not equal because they're not equal. Shoot, I'm not going to have enough room on that. So, then you go to 1/2 mv initial squared, 1/2 mv initial squared. I'll add in my 1's and 2's in a minute. V final squared, and V final squared, 2211. This one still goes to 0. So now you just fill in all your numbers. 0.25 kilograms. This was 5 meters per second. What gets squared here? Just the 5. It's just the V. 1/2 0.25 meters per second. 2.619 meters per second. And I guess you can put the negative there if you want, but remember it gets squared, so it really doesn't matter. Plus 1/2, I'm going to run out of time. So close. Kilograms, this is really a kilogram. Times 2.3809375. squared. And now you're going to punch this in before you start the